Hello everyone, welcome to this video. My name is Emerson Ahari. I'm a Google Earth Engine expert. In this tutorial, I'm gonna show you a relationship between urban growth and urban air quality using Muddy's product in the Google Earth Engine platform. In the first step, you must select your region of interest. For example, I'm gonna select an urban area in Iran. It is capital of Iran, Tehran. It is a populated region with more than 10 million people residents. So if you go to the satellite, you can see urban borders much better than what we have in the map. Using drawing tools available here, I'm trying to make a rough estimation from a border. So as you can see, I'm drawing the border of the urban area quite roughly, and also with low accuracy. So as you can see, if you have the shapefile for the urban area, that is better to use the shapefile for the region of interest. Otherwise, drawing tools can be also a helpful way to actually draw your region of interest here. So to have focus on the study area, map.center object allows us map.center object like this. According to the geometry, the region of interest here named as a geometry. To have focus on the study area, map.center object allows you to focus on the map on the study area when the code is running. So next, we want to detect the urban area and assess the urban area variation during the time over the last 20 years to see how much urban growth over the last years. So the simplest way, go to the search places and dataset and try for Muddy's land cover product. Muddy's land cover product is available since 2001 with annual frequency and 500 meter, and this is the simplest way that you can calculate the urban growth or urban development over the last 20 years, imported into the code as an image collection. So assigning image collection to the urban, and no need to filter based on the geometry or the date, because I'm gonna use all the land covers available from the start time to the end time. If you go to the data description, you will see this data is available since 2001 so far. And also if you go to the bands, here different land cover standards are available. For example, I'm gonna use LC type 1 in this tutorial because this is the most common or most typical layer that people or community use for the land cover assessment using Muddy's data. And if you want to know about the LC1 table of contents, here there is a class table that shows the relationship between each numbers in the land cover and also the corresponding class and description here. As you can see, the urban area actually visualized by the pixels numbered as 13. So as you can see, now in the next step, I'm gonna select the LC type 1 and then make a code to calculate the area for class number 13 for each year separately to see how much urban growth in this region over the last 20 years. As I mentioned in the previous tutorials, .select is a function allows you to select the target band or desired band. That here is LC type 1, just like that. So print urban to make sure everything going well. So in the right panel here, one image collection with 23 elements available. 23 elements here, each one of them belongs to one single year starting from 2001 ends to 2023. If you go to the pans, here LC type 1 is available with couple of properties that is necessary for the time series analysis. So in the next step, I'm gonna make a loop to calculate the urban area for each one of the elements available under image collection. So make a map here. As you know, in the Earth engine, the map works as a loop and it allows you to make a loop and also those in which you can make a function to apply a single or couple of equations on each elements you have under collection. So in the map here, each one of the every one of the elements that you have here entered to the loop structure through the map, and now we want to call them with a single name as ing. So to do the calculation, first for each input image, I'm gonna select the pixels including urban area or including number 13. So here there is a threshold. From input image, I'm gonna select those pixels equals to number 13 because the number 13 reflects urban area in the land cover map. So now the threshold actually is a kind of binary image with 0 and 1, in which 1 shows the urban area and 0 non-urban area. So in the next step, I'm gonna mask the non-urban area from the threshold image. Another layer as mask is created equals to from the input threshold, we want to do update mask based on the threshold. In this expression, the threshold the pixels with 0 values removing from threshold image. So finally, in the next step, the area of remained pixel or the area of urban pixels should be calculated under area variable. The mask layer dot multiply Earth engine dot image dot pixel area. Generate an image. As you can see in the description, the pixel area generate an image in which the value of each pixel is the area of that pixel in a square meter. It is very important. So now I'm gonna calculate the area of each pixel based on a square meter. And if you want to convert it from a square meter to a square kilometer, that's divide 1 million. So this is a simple equation or simple conversion between a square meter and a square kilometer. Finally, the function returns the urban areas with their the urban region with their area. Return area. And finally, the properties of input images should be copy and paste for the output. And also among the input properties or the properties we have in the original data, only system time start and system time end is necessary for the next step and time series analysis. That's why writing system time start and system time end here. Actually, I'm selecting a couple of properties for the further analysis. The date acquisition always mentioned with system time start and system time end that is necessary for the time series analysis in the Google Earth Engine platform. So if you get a print from the airband in the right panel, you will see still we have 23 elements, but this time we only have the urban area without any other classes in which the area of each pixel already calculated. So now I'm gonna make a chart or make a plot, two-dimensional plot that shows the variation of sum of urban area since 2001 to 2023. Another print created here, just like this. Print, user interface, chart, image.series enables you to plot the sum of area of urban region from 2001 to 2023. Instead of image collection, we will have the urban. Instead of the region, we will have geometry. And now the reducer is important. As you know, the reducer is a statistical operator, allows to calculate or aggregate time series based on the allows you spatial aggregation based on a statistical operator such as sum, mean, max, average, whatever you want. So, and here Earth engine.reducer.sum, because I'm gonna calculate the total area of urban pixels over the selected region. So, and the scale equals to the spatial resolution. As this data has 500 meter, that's why the scale should be 500. Instead of X property, we should have system time start explaining the acquisition date for the land cover data since 2001. Remember to save your code and run it again. After a few moments here, you will have a plot that shows the area of urban structure or urban development over the last 20 years. As you can see, there is a clear increasing trend in the urban growth in this region. Now I'm gonna see that in the next step how much urban growth correspond with, for example, the air quality and aerosols over the urban area. Because as you know, the aerosols created by industrial activities or human activities and fossil fuels and air pollution over the urban area and causes a lot of effects or negative impact on the people who are living in that area. So in the next step, make another variable to for example aerosol data. So here I'm gonna use aerosol optical depths that is available in Modis product. If you go for Modis AOD, here you will find Modis land cover product with 1 kilometer spatial resolution and then import it into the code as a second image collection. So assigning the second image collection to AOD. So then filter your data based on region of interest and also the period of time you want to work in. For example, now here I'm gonna make a time start and time end, because in the next step I'm gonna convert this data to the annual structure or annual frequency that enable me to actually compare it with urban growth over the same period of time. So here I will have Earth engine.date to convert a string from a normal string to date format. The time start equals to 2001 and time end equals to 2024. But as you know, the 2024 is not the last year. The data limited to the end of 2023. So then filter your data based on time start and time end, just like this. And remember to use filter bound for the region of interest. As I mentioned earlier, for the coarse spatial resolution data, it is not necessary to use, for example, a filter bound because there is no framing structure. However, in the MODIS data, it is for the MODIS AOD, it is necessary because this is the exception. So, and also bound, I'm gonna filter data based on the region of interest that's already named as a geometry, and you can see here. If you go to the data properties here over the bands, you can see two bands available for optical depths. One of them is for 470 nanometer, and another one is around 550 nanometer. Actually, the smaller optical depths always used for the urban area, that is very helpful for the dust or aerosols that is detectable over the urban region. That's why I'm suggesting to use the smaller optical depths for the urban area and the larger optical depths for the non-urban area. So this is that could be a main difference between the optical depths 47 and optical depths 55. So because we have a smaller aerosols in over the urban area, and a smaller wavelengths can be used for their detection. And also remember, there is a scale factor here that should be considered before doing further analysis. So the optical depths 47 is the target band. Back to code and select the target band using select function, just like that. So now I'm gonna convert. As you know, this data is the MODIS AOD product has daily frequency, and it is very important to convert it to the annual format. That in that case you can compare it with the urban growth over the same period of time. So first of all, we must make a list of values starting from 0 and ends to the time end based on the number of years we have from time start to time end. So a new variable created to calculate the differences between time start and time end. We want to calculate to see how many years do we have from end to a start. So here we have time difference, or you can have it as a year, no difference. So time end dot difference. Difference is a function that returns the difference between 2 days in a specific date. This is very important. Two arguments we have here. One of them is the start and one of them is unit. The start equals to time start. As you can see, it started from time end, and then we will have the time start. And the unit could be different things: minutes, days, month, and year. And here I'm gonna calculate the number of years we have from time start to the time end. Make a print layer to see how many years do we have from time start to time end. 22.9. We must round it because we want to have the number of years. So that round is a function that round the values to a bigger number. As you can see here, we have 23 years from 2001 to 2024. So in the next step, make a list of numbers starting from 0 to 22. So here we have a list of numbers equals to first engine.list.sequence. As you can see, couple of arguments in this list must be considered, starting from 0 and end to the number we have in the time difference. So the step is 1 because we want to have a list starting from minimum to maximum and increasing one by one. So skip the count and make a print from list. In the right panel, you will have a list with 24 elements starting from 0 and ends to 23. But in this case, we will have 24 images that is different with or against time difference, because we must have 23 elements here. That's why it is important to subtract the time difference from 1 because the list is starting from 0. In the right panel, the problem is solved and the list is starting from 0 to 22. In the next step, I'm gonna replace the date or start or the year of actually each image, instead of having only simple number from 0 to 22. So make a map because I'm gonna do some sort of calculation on each row separately. That's why we need to make a loop through the map. For the calculations, a function needed. Each import row in the actually calculation could be anything. For example, we can have it as an I, for each row can be called as an I, or each row can be called as a delta for the year that can be calculated. So here, and function returning, as you can see, the function returning from time start, go advance, so couple of arguments, go advanced based on the imported delta already defined, and the unit should be year. We are going forward according to the delta values already defined here based on year unit. Save your code and run it again. In the right panel again, there is 23 elements, but this time instead of delta values or the simple number, you will have a list of dates starting from 2001 and ends to 2023. So in the next step, I'm gonna define the time start and time end for each list separately, and then calculate the number of dusty days over the last 20 years for each year separately, and see that how the dusty days changing from 2001 to 2023. A new variable as dust or AOD or something like that, dust frequency. For example, here I'm gonna calculate the frequency of dust. That's why the name should be frequency or occurrence or something like that. Equals to Earth engine.image collection. First of all, bring your calculation inside the image collection because the output must be an image collection format, because finally we want to have it as a chart. We want to have its value as a chart starting from a year to another year. It is important to have an image collection as output. As you remember, Urban was an image collection. That's why we used Urban in the image.service. So inside the image collection, bring the list first and make a loop, because for each row, for each date separately, we want to calculate the end date and also calculate the number of dusty days or number of dust occurrence or aerosol occurrence from start to end. To do this, we need a function inside the loop, and each input to the function is a date. So here, now already a start date defined. Here we must have a start date that is equal to the date. As you can see, we already have the start date and there is no worries. So, and then we want to have the end date. How we can calculate the end date? The end date is for example, starting from 2001 and end to December 2001. So from start date, it's very simple. From start date, go advance according to a delta, and delta is 1 and the unit will be year. We want to go forward from each year to 1 year later to calculate, for example, everything you want in the next step. So what we want calculate here, this is occurrence, the AOD occurrence or dust occurrence. Dust equals to, so already AOD data defined through the AOD variable. Bring AOD variable here and filter it based on the each year period that's already defined through the start date and end date. Start date and end date, just like that. So now here we are filtering each AOD, the AOD data for each year separately through a loop structure. Now I'm gonna do some sort of calculation for each year separately. Another loop is created with a function. This time the images are importing to the function structure. That's why naming as an image. First, a new variable as a bands calculates the, for example, the scale factor, or applies the scale factor on each input image. From input image dot multiply or 0.001, I think. If you go to the data description here, go to the bands, yes, this is the scale value we have for the optical depth images. So then there is a threshold for AOD. As you know, there is a linear relationship between AOD and dust in the air quality concepts, and also there is a threshold that make a difference from a dusty situation to a non-dusty situation through the AOD, and this is 0.5. So here I will have a threshold in which it is all the pixels greater than 0.5, meaning that that pixel is dusty. So bands.gt 0.5 greater than 0.5. Here we will have a binary image in the threshold that in which the dusty pixels shows with 1 and also the non-dusty pixels will have 0 values. Finally, the function returning the threshold image here and we get the sum of the actually dusty days for each pixel separately. This is very important technique. So finally we're back to the frequency variable we were working on. As you can see, now for each year we have a start date and end date, and for each start and end date the number of dusty days calculated through the threshold we defined here. And now the frequency should return the dust image as a final output. Another return belongs to the first map, or the final return belongs to the first loop structure. Return dust dot copy return dust with new system time start and new system time end, because now the temporal frequency changed from daily to annual. That's important to have new time start and new time end here. So that's set system time start equals to start date dot millisecond dot set system time end end date dot millisecond again. It is very important. So, and if you want to have a new system index, you can define it here. A new system index equals to the start date, explaining or showing the date of each image with the normal format. Dot format convert it to the string with this structure: year, month, and the day, just like this. Get a print from frequency. So here should be a start date. T was missing. In the right panel again, you will have 23 elements there that each one of them shows the number of dusty days over the, for example, last 20 years. For example, here, if you want to see how the dusty days changes alongside to the urban growth in this region, you can use another chart structure: user interface chart image.series. Instead of image collection, you will have frequency. The region is geometry. Now we want to aggregate the frequencies to the average. We want to see that what is the average frequency or average dust occurrence for each year over the region of interest. Earth engine.reducer, this is a spatial aggregation. Dot mean, and the scale should be 500 meter because the spatial, 1000 meter because the spatial resolution is 1 kilometer, and X property equals to system time start. Run a code again, and in the right panel you will see a new chart that shows the number of dusty days starting from 2001 and ends to 2023 alongside the urban growth. That maybe takes a little more time. As you can see, the chart is under generating. If you faced or if you had any problem regarding to the code, you can find the code example link below the video in the description box, and then you can compare yours with mine. If a still problem exists, you can reach me out on YouTube channel. I'm highly asking you to send your message through the YouTube channel because there are lots of messages in the email and also in the LinkedIn, and also it is difficult to handle all of them. That's why I am asking you to send your message through the YouTube and comment session. So as you can see, there is a problem about the system time start, and T is missing here again. Run a code again. In the right panel, we are waiting for a new generating chart. And there are a lot of tutorials on my YouTube channel, and I'm suggesting you, and I'm always recommending to see all of them because different techniques and materials available in each video that helps you to learn more and more about the Google Earth engine, and then you can improve your skills in this regard. Because Google Earth engine is not only limited to the techniques I'm using here. It is more than what we are saying here, and I'm trying to show you different techniques from one tutorial to another tutorial. So as you can see, there is an increasing trend in the number of dusty days. For example, in 2023, we had 18 dusty days in which the RSL value was above 0.5, and also in 2002 we had 29 days in which actually on average the dust situation or RSL value goes above the 0.5. And also such kind of plots are very important and gives you insight about the what's going on over the urban area, and regarding to the urban development and regarding to the urban air quality. Such kind of outputs are very important for the further analysis. And finally, if you want to save the if you want to have raster layers for the frequency or for the land cover, it is a very simple technique to use export.image to drive, because most of the users asking me about how to get export from all of the image. I'm always suggesting to go through all tutorials, because all of them including different techniques that highly helps you to increase your knowledge about the Earth Engine functions and techniques. And also don't limit yourself to only one video, and let's try with different tutorials, because this is the most important way to empower your abilities in working and dealing with the Earth Engine. Exports.image to drive. The image or the target image, for example, is the frequency converted to the, for example, the stack layer, and clip it based on the geometry that you have here. So, and the description, the output name, for example, could be AOD dust or anything you want to have, no difference, and a scale or pixel size equals to 1000 meter, because the spatial resolution is 1 kilometer, and the region of interest is equals to the geometry, and CRS coordinate system equals to EPSG 4326. This is for WGS 84, and same for all around the world. And another thing is, you can use this tutorial for all around the world, and it is not limited to only one specific area, because the platform is actually the free Google Earth Engine, and also the data, satellite data and techniques are usable for all around the world, not limited to only one specific location. The only limitation is the temporal period, that data starting from 2001. If you want to use actually MODIS layer for such kind of research and investigations. And and if you want to save your data in a, for example, particular field, a folder on your Google Drive, here you can make a new folder as for example, test and try for and then save your data in. So this is a very simple technique to get an export. If you run a code in the right panel under task, you will have a new task as AUD dust. Just click on run and run again, and now you must wait until AUD dust created or saved on your Google Drive account. And once the tab's color turn to the, oh, seems there is a problem, convert the image to the floating point number. Yeah, that's the problem that sometimes happens. That's why here that clip that float to solve the issue. Run a code again. As you can see, if there is any problem, the color tab turned to the red. But if there is no problem, and also if they say if completely saved in the Google Drive, then turn to the blue color. Run it, and again run. I'm waiting to see how progresses. Seems there is no problem now, and yes, the problem is solved. And so I hope you like this tutorial as much as I did, and I tried to give you insight about combining different data in the Google Earth Engine platform to see that how we can use different products to extract information from different kind of data we have. One benefit in remote sensing is that you're not actually limited to only one data or one product. You can use various kind of products and information and compare their values to each other, and this is and gives you a good insight about informative insight about what's going on the earth. So if you had any problem or questions, feel free to reach me out on YouTube channel and put your comments there. I will try to check and answer them as soon as possible. Thank you for your attention.